Hello everyone. My talk started out being about the ring slice method we developed for MPMS Chapter 2.2a, but upon reflection I realized the diversity of the audience requires me to step up to the game and make this talk appropriate for a group like this, interesting, informative, and possibly useful. You can see that the title of the talk reflects this look back. I do have one slide at the end about the ring slice method for calibrating tanks, however. There are a few themes in this talk. Of course, as the title suggests, the major theme is about how standards can stifle or how they can spur innovation. Everyone here knows how Hercules had superhuman strength like Superman, but these heroes only exist in our imagination. How does an individual or small company or any entity make a difference? We'll talk about that too. Finally, standards are dynamic, although they sometimes do not seem to be. A snail may seem to be static, but it can get from one side of your yard to the other, but it might take a day or two. Some of the examples I present you show the incredible changes that standards have seen over the space of just a few decades. One important tool used in the construction of Egyptian pyramids thousands of years ago was the royal cubit, an ancient tape measure used by ancient engineers in the days of yore. The Egyptian pyramids are accurate to within 4 minutes of arc, or 1/15th of 1 degree, when aligned along the cardinal points north, south, east, and west. So I ask you, did standards help? 40 feet under Gaithersburg, Maryland, is a vault that requires 3 different keys to get into. What's in there? The vault has a collection of shiny metal cylinders that define the mass of everything in this country. The vault belongs to the National Institute of Standards and Technology, better known as NIST. The inset on the right shows a copy of the original International Bureau of Weights and Measures kept at Sèvres, France since 1889. It is called the International Prototype Kilogram. Its nickname is Big K. Copies of it are used all over the world to calibrate scales. The problem is that Big K lost 50 micrograms since it was created, and therefore the mass of a kilogram has changed and scientific chaos ensues. But this all changed as of May 20th, 2019. The new system is based on Planck's constant. The kibble measures the downward pull of a gravitational force on a mass by counteracting it with an upward electromagnetic force. The same kind of standards evolution has occurred with a meter. Originally, it was a length of a bar at the Bureau of Weights and Measures. Now it is defined in terms of the speed of light in a vacuum. Incidentally, 4 of the 7 SI base units were redefined in 2019: the kilogram, ampere, Kelvin, and mole. Kelvin is defined by the Boltzmann constant instead of the triple point of water, and the mole is now defined by Avogadro's constant. This is a good example to show why API standards are reviewed every 5 years. A standard is an agreement that permeates society through commerce. It promotes precise communications and efficient business transactions. But there are fundamentally different types of standards. There are simple and well-defined standards like those of measurement, but there are other categories, for example, prescriptive and performance-based standards. Yet others are based on the term interoperability, such as how hundreds of different modeling and CAD programs can exchange data. In our finite element modeling work, we use step files for models when exchanging models with other engineering organizations. We also use ASTM E57 for laser scanning data exchange. It is easy to see the importance of standards in this case. Pilots in a Korean air freighter plane became confused about whether the units were in feet or meters, leading to a crash resulting in fatalities of the crew and on the ground. The benefits of standards are obvious. The negatives of multiple standards that do the same thing, such as SI or USC, are also clear. The SI standard is the world's basic standard for measures, but for many reasons the US is still a holdout. I remember in college when professors would say that when the old guys die off or retire, the SI system will be used in the U.S. Well, that time has come and gone, and we are still waiting for the day when SI will be universal. Here is another example of problems created to which standards are being used. In this case, there were two teams of engineers working on the launch of the Mars Climate Orbiter in 1998, which cost about $125 million. It was lost because one team was using metric and another was using SI. Ultimately, standardization allows for precise, clear technical communications between individuals, groups, and nations. You are all familiar with the QWERTY keyboard. This is an example of a de facto standard. A de facto standard is a standard that has become accepted through practice or tradition, but has not gone through a formal process to gain consensus. De facto standards can be formal or informal and may not have an official standards document. Here is a look at categorizing standards. You can have fundamental standards such as the U.S. customary standard for units. You can have prescriptive standards such as the speed limits on highways and roads. You can have performance-based standards setting targets such as limiting the amount of air emissions coming from a storage tank. Finally, you can have interoperative standards discussed previously. There are other ways to classify standards. For example, de facto standards, or those that arise from regulations. You can have consensus standards such as those that we will all work on intensely this week. The infrastructure of commerce is pervaded by standards. This includes economic advancement, national security, and globalized trade. It is interesting to note that the government in Europe and elsewhere are typically more supportive to standards development than what happens in the U.S. So on to the basic theme. Do they help, hurt, or are we undecided? I hope the following examples will shed light. Of course, my own belief is that they help, but that's just a personal opinion. You can decide for yourself. The picture on the left is a so-called membrane tank, which is inside a marine vessel for shipping LNG across the oceans. On the right is an LNG storage tank. LNG makes up about 25% of the total energy supply worldwide and is projected to keep that proportion until about 2050. I have been working with PHMSA to develop a new tank inspection and repair standard for LNG tanks, very much like API 653 for conventional oil tanks. While the membrane tank is one of many designs, it cannot be used in the U.S. Why is that? The simple answer is that the government, through its PHMSA agency, is codified a 20-year-old NFPA standard that does not include membrane tanks. The last several editions of NFPA 59A for LNG tanks do indeed allow these designs. The bottom line is that PHMSA has baked in obsolescence by using out-of-date standards. This, of course, stifles innovation and is an example of how standards can squelch development. I have complained to people who work at DOT about this, but the answer has been, we don't have enough staff to review your work, and by the way, we don't trust you, or we don't have the funding. They are well aware of the problems they create. Another example is risk-based inspection for storage tanks under DOT rules. It's not allowed. Now I want to move on to a far more significant standard, the Montreal Protocol. Certainly, it was one of the greatest standardization efforts of all time. Here is the case where regulations and industry in a monumental standardization effort unified the globe to make a huge beneficial change for us. Today, we and our future generations inherit the benefits of the Montreal Protocol. Interestingly, the brilliant chemist Midgley played a major role in leaded gasoline as well as chlorofluorocarbons, CFCs, known as Freon. Both have been banned, as you know. In 1944, he was found strangled to death by a device he created that allowed him to get out of bed unassisted. Environmental historian J.R. McNeill stated he had a more adverse impact on the atmosphere than any other single organism in Earth's history. He was also called a one-man environmental disaster.
1980s. The 80s were all about big hair, neon, MTV, and then there was this.
Every October, a hole appears in the ozone layer over the South Pole.
The hole in the ozone shield is the size of the continental United States.
The protective ozone layer is being threatened as never before. We're all at risk.
Scientists warned that humanity was on track to completely destroy the ozone layer by 2050. Without it, ecosystems would collapse, skin cancer rates would skyrocket, and life as we know it would cease to exist. But today, the ozone layer is healing.
Short wavelength UVC is the most damaging type of UV radiation. However, it is completely filtered by the atmosphere and does not reach the Earth's surface. Medium wavelength UVB is very biologically active but cannot penetrate beyond the superficial skin layers. It is responsible for delayed tanning and burning. In addition to these short-term effects, it enhances skin aging and significantly promotes the development of skin cancer. Most UVB is filtered by the atmosphere. The relatively long wavelength UVA accounts for approximately 95% of the UV radiation reaching the Earth's surface. It can penetrate deep into skin layers and is responsible for immediate tanning effects. Furthermore, it also contributes to skin aging and wrinkling. For a long time, it was thought that UVA could not cause any lasting damage. Recent studies strongly suggest that it may enhance the development of skin cancers. On the left are two ozone molecules made up of 3 oxygen atoms each. On the right is Freon, or a CFC. The green atoms are chlorine. The chlorine acts as a catalyst, and one chlorine atom can break down hundreds of thousands of ozone molecules. The ultraviolet radiation in the atmosphere will come in and break out the chlorine from the CFC. The one chlorine atom is converting the ozone to oxygen, O2. As you can see, the public, through their industry and regulatory representatives, forced change. Amazingly, the world was not divided then on this issue. The science was clear. Every industry signed the treaty. It is an example of the most important and successful environmental achievements ever implemented. This shows essentially 100% agreement by the various signatory countries of the Montreal Standard. Here, ozone-depleted substances, or ODS, decreased sharply with the new standard in place. This shows the actual size of the ozone hole in square kilometers measured at a concentration level that is at about 50% of average. Note that the hole size increased up to about 2,000 and then started to taper off. But what is the huge spike at the end just a few years ago? We'll see what caused that next. The Hunga Tong Hunga Ha'apai eruption occurred in January of 2022. It ejected a 58-mile-high plume and was the biggest atmospheric explosion ever recorded, dwarfing even the largest nuclear weapons. It is believed that the spike in the size of the ozone hole is related to this event. You'll see the event occur in this area right here. It's hard to get an appreciation for the size of that explosion. At its largest diameter, it would fill up pretty much all of Europe. These are actual satellite pictures showing the event. ODSs are ozone-depleting substances found in aerosol cans, foams, and fire extinguishers, as well as refrigerants. There are 2 classes. Class 1 includes fully halogenated CFCs, halons, and the ODSs that are the most threatening to the ozone layer. Class 2 includes hydrofluorocarbons, HCFCs. Although being phased out, it is clear that HCFCs are still being released in significant quantities to the atmosphere. This map shows the contributors to ODSs by country. Hydrofluorocarbons, or HFCs, don't directly aggravate the ozone hole, but they contribute to warming the atmosphere and causing the reaction rates to speed up. Their contribution is very small compared to chlorine-containing CFCs. This graphic shows ozone depletion in terms of this axis. Here's no depletion and less ozone. That's bad, so going to the left. You can see the year count here, and this faint blue is the depletion of ozone due to the HFCs. As shown, there are a number of rules to limit the use of HFC emissions. In fact, the Montreal Protocol committees still meet and modify it in an attempt to prevent aggravating the ozone hole. For example, the Kigali Amendment addresses HFCs. This meeting looks really familiar, except that they don't appear to be getting breakfast like we do. Here is the final example of standards and innovation. It involves telecommunications and mobile communication standards, where both the stifling of innovation as well as the amplification of innovation have occurred. Or SDOs for the telecommunications industry. The FCC is one of them in the U.S. It controls the licensing requirements for radio transmission and controls the radio broadcasting attributes listed. The International Telecommunications Union Radio Communications Sector, or more simply ITU-R, is a standards organization that coordinates the allocation of the radio spectrum globally. The world is divided up into regions for this. Within each region, the governments regulate the RF spectrum. An example of one of the standards from this organization is ITU-T G.709, which is a standard for optical transport networks. IEEE is best known for LAN standards. For example, IEEE 802 Task Group wrote the Ethernet standard. They are also responsible for the 802 standards such as 802.11a, 802.11g, and others. Many people think Wi-Fi is a short form for wireless fidelity, but it's a bit more complicated than that. The term cropped up in 1999 as a more user-friendly way of describing the wireless standard IEEE 802.11 by a marketing firm sometimes referred to as the Wireless Fidelity Alliance. The G in wireless specifications just means generation, and it isn't even good at distinguishing that. Marketing hype leads vendors to show improvements such as LTE for long-term evolution and 2.5G and 2.75G. Analog mobile radio communications of the 70s and before were often called 0G. You can see a 0G setup. It's so big it barely fits in the trunk. They were also so large that you'd have to carry a box to lug it around. 1G is still used for analog signals. In 1992, 2G allowed for true digital wireless transmission and the first SMS text messages. In 2001, 3G allowed data, voice, and video. In 2011, 4G was rolled out with speeds of 10 to 100 megabits per second. IP protocols were also rolled out then. 5G was rolled out in 2020, and 6G is expected to be in operation around 2030. It is interesting to note that the IEEE Wi-Fi standards appear to come and go at about a 5-year interval, which is similar to our standards. There is an incredible amount of development always going on in the wireless field. Not only have wireless speeds gone up by orders of magnitude in just a decade, but the high rate of reliable transmission drives the need for higher frequencies. Information is limited to the frequency, so that the conventional band for 4G has been opened up to the so-called millimeter wavelengths, as you can see, with a range from kilohertz to 100 gigahertz. These high frequencies are needed for remote vehicles, remote surgeries, healthcare, and so on. Latency must be low and the speeds must be high with high reliability. To achieve the need for more and more wireless communication requires innovations such as beamforming technology and even using signal bounce. Full duplex communications on a given frequency are now possible, which increases the spectrum efficiency by a factor of 2. Encoding more information is possible with higher frequencies and new ways to modulate the signals. Each one of the squares in the picture is an antenna. Base stations can be retrofitted with antenna arrays, making it possible to get 1 million devices per square kilometer in a single cell. One word about one significant historical event. In the 1980s, Dr. O'Sullivan was studying black holes for the Australian science agency CICERO. CICERO did not yield the desired results for the black hole studies, but in the 90s, O'Sullivan tackled the Wi-Fi cabin problem. This is basically indoor Wi-Fi signals that bounce around, and the received signal has echoes and distortion which limit the signal speeds. At the time, there were 22 other research projects attempting to solve this problem. O'Sullivan and CICERO invented a chip that was a small and fast chip sufficient to be used in cell phones. It enabled the cell phone technology as we know it today. Although it was patented in 1993, the major players ignored it and developed their business without regard for the patent. In 1999, the IEEE incorporated the method. In 2002, CICERO demanded licensing royalties for the technology. Dell, Intel, Microsoft, Netgear, Apple, and others sued CICERO to invalidate the patent. In 2006, CICERO countersued. The showdown occurred in 2009 in Texas. 14 of the most powerful computer companies in the world versus CICERO. They all ended up settling. At this point, I want to give thanks to everyone in the standards industry who actually makes a difference in the lives that we lead and the betterment of society through standards work. This launches me into the final point. In spite of how significant or trivial the change in standards seems, they are happening all the time. The totality of the small changes lead to major changes with time. I would like to illustrate how a need combined with a little imagination and perseverance can lead to some innovation, in my personal case, by the next example. We first have to start with the idea of a Fourier series. Basically, this series allows one to make any periodic signal of any shape with a simple addition of sines and cosine waves. The function argument is an integer multiple of the lowest frequency. Basically, what this is saying is that you can recreate any waveform whatsoever by a series of sines and cosines. Harry Nyquist came up with the important theorem that for a bandwidth-limited signal, if you sample at least twice as high as the highest frequency, you can completely recover the signal. This is best explained by an example. If you want to digitally record music, for example, you have to sample at twice the highest frequency of the bandwidth. Human hearing is capable of 20 kilohertz, but probably most of you out there would be lucky to hear 10 kilohertz simply because you are not a teenager. This means the sampling rate has to be at least 40 kilohertz. The actual sampling rate is about 44.1 kilohertz in digital music. There are technical reasons why the sampling rate is a little higher than 40 kilohertz, but we need not go into that now. In the past, elevation measurements around the perimeter of a tank were made using 8, 16, or sometimes 32 points. But today laser scanning is coming, and there are usually several thousand points on the chime or at the base of the tank. How can the methods of API 653 be used? The short answer is they can't. API 653 already uses the idea of a cosine wave. It occurred to me that the bottom elevation is nothing more than a signal, and it is periodic as well once you get once around the circumference. This means that Fourier series applies to it. We also know that very high frequency content, meaning curves that are over a very short distance, like dents caused by forklifts running over the bottom when it was built, is not settlement but is noise. So the Nyquist limit applies, and we can limit the frequency to those that are valid for tank bottom settlement. In addition, this tells us how many terms of the infinite series we actually need. We'll see this better on the next slide. A plane tilt, if plotted on a graph paper, turns out to be a sinusoid where the amplitude is a total tilt. You can see that illustrated here. Here we are using laser scan data to analyze the differential settlement of a tank bottom to see if it is excessive. By using many sinusoids according to Fourier, we end up with the ability to perform sinusoidal regression on the data. In this case, there are several thousand points. By limiting the frequency to the Nyquist limit, we limit the possibility of overfitting, which is not a good thing in modeling. In this case, the black curve shows the regression fit, and the red line shows the second derivative, which is a measure of curvature of the bottom. Curvature is already limited by API 653, and we simply limit it to the existing criteria. The dotted lines are the limits of curvature allowed by API 653. So in this case, because the red line is below the dotted red line, the tank passes the settlement analysis. This item is now in ballot. It had one negative which we resolved, and it is going to ballot again. Because the topic is a little complicated, we have written demonstration papers and illustrated how to code up this problem so that the industry can readily adapt to this methodology. Here's another small evolutionary change for API MPMS Chapter 2.2a on tank calibration. In reviewing 2.2a, it was obvious that it was very difficult reading, not transparent, and heavily depended on the expansion of the tank shell caused by hydrostatic pressure. It occurred to me that since we do a lot of finite element analysis, it would be easy to check the methodology. It turns out that it was actually very clever and ingenious, but not transparent. Rather than trying to fully understand how the people that wrote Chapter 2.2a did it, we used FEA. You can see that the real growth in the tank diameter is on the left plot. By using a simple linear scaling between courses to simplify things and to make sure that FEA is not required for the tank calibrator, we checked the simple linear fit. It turns out that it is more accurate than the current 2.2a and is much simpler and, of course, more transparent. A 2.2a task group is setting up the work so that it can be implemented right now. This is the end of the foray into the world of standards. I hope it provides a little bit of perspective for you. Thank you.